Hi, I'm Tom Sherlock. I work in the user interface group here at Wolfram Research, and today I'm talking about stellar aperture photometry.
Okay, let's get started. As you can see, my name is Tom Sherlock. I'm a user interface developer here at Wolfram Research. I'm not a professional astronomer. That's my hobby, and so for the last several years I've been talking about different aspects of astronomy and astrophotography. And previously, my talks have been basically devoted to improving the images I've been taking with my telescope and trying to get better, pretty pictures. Well, today's talk is going to be more concentrated on getting actual data out of astronomical images. So it's going to be a little more data-centric. So what we're talking about today is stellar aperture photometry, and this is basically the technique of pulling brightness data out of a series of astronomical images of a star. And there are many reasons why you might want to do this. You can learn interesting physics from the light curve of a star, including things like, for instance, how far away the star is, or if the star is an eclipsing binary, you can learn things about the dynamics of that system, or if the star is being eclipsed by an exoplanet, you can detect exoplanets that way. So there's a lot of very useful and interesting information can be gained by extracting light curves from astronomical images. And as it turns out, Wolfram language is an ideal package, an ideal tool for doing this, because we incorporate a lot of different things which are useful to astronomers. There's a lot of image processing machinery inside the Wolfram language, and also we have the ability to import astronomical data and then do analysis on it. So I'm going to talk a little bit about some of the things I've tried here, and we'll see how far we get. So today we're going to talk about CCD photometry. In the olden days, photometry was basically you would hire a bunch of people and they would look at big glass plates and try to estimate the brightness of stars on the plates using microscopes and stuff. Today we have CCD cameras, so we can actually just bring the data right into our analysis system. And so we're going to do this and create a time series of data. And the example I'm going to use has to do with the class of variable stars called Cepheid variables. Cepheid variable stars are interesting because there's a strong correlation between the star's light curve and the star's intrinsic brightness, or its absolute magnitude. This period luminosity relationship, which was first published in 1912, is called Levitz Law, after Henrietta Swan Leavitt, based on her work at the Harvard College Observatory. She was one of these people who crunched data in the early part of the last century by reading it right off of glass plates. And this is about the definition of tedious work as far as I'm concerned. And eventually, Henrietta worked her way up to being paid 30 cents an hour for this. Initially, she wasn't paid anything to do this. But what she determined was for population 1 Cepheids, there's a simple relationship between the star's intrinsic brightness, its absolute magnitude, and the period of its light curve. So they're related by log base 10. So this is called Levitz Law, and we can write in Mathematica as absolute magnitude is negative 2.81 times log base 10 of the period. The period is measured in days minus 1.43. And there's more complex versions of this formula if you want to incorporate observations made in infrared and visual bands. This is basically just the simplest form of it. So that's what we're going to use right now. So to give an example of this, absolute magnitude of a Cepheid with the 3-day period is going to be negative 2.778, quite bright. And this is a log linear plot of absolute magnitude of the period. You can see it's just a straight line when plotted on a log scale. So if we have a measure of the absolute magnitude of the star, and since we know that brightness falls off as increasing distance from Earth, if you have the absolute magnitude of the star and the apparent magnitude, which you measure from Earth, you can get a pretty good estimate of the distance in parsecs of the star. And this is just a power relationship. So you subtract the magnitudes, add 5, divide the sum by 5, and raise that to base 10 power, and that will give you the distance in parsecs. So we can combine the two formulas and get a relationship which will give you the distance in parsecs from Earth to the Cepheid based on its apparent magnitude observed from Earth and its period in days. So we're going to try to perform this calculation. Before we go any further, we should also mention Edwin Hubble. So in 1924, he used this relationship to make a very significant discovery. He found one of these Cepheids in what was then believed to be the Andromeda Nebula, which was thought to be part of our galaxy. This is, if you go out on a dark night, like in the summer, you can see a patch of light in the constellation Andromeda. It's near the Great Square of Pegasus. And this was thought to be part of our own galaxy, and the whole universe was considered to be part of our galaxy. But Hubble discovered one of these Cepheids in the Andromeda Nebula, and by using this period luminosity relationship, he determined that that star was 2 million light years away. So the Andromeda, sorry, I'm getting over a cold. The Andromeda Nebula is actually a whole new galaxy. And he did this with other galaxies too. And that greatly increased the span and the perceived size of the universe. So if we do this, we need to make some prior work. We're going to start with a set of image frames. And they need to have some bits of calibration done to them. And I've talked about the calibration process in previous talks. And basically, we would have to subtract out noise and try to flatten the frames out so we can make comparisons between stars in different parts of the frame. So we have to subtract out the dark noise, and we need to subtract out flat frames. And they also need to be pretty well lined because we're going to be doing like pixel by pixel comparisons. And we'll talk a little bit more about the alignment later in the talk. And there's also another type of noise called bias noise, but we don't have to worry about that for this sort of calculation because that just gets subtracted out when we do the photometry. So the basic technique we're going to use is we're going to divide the area around our variable star into 3 regions. And the star itself is going to be inside the center red disk, which is called the star aperture. And we need to get an idea of what the intrinsic sky brightness is behind the star because that would interfere with the signal. So we have to subtract that out. And that'll be measured inside the blue annulus, which is called the sky annulus. And to separate the two, we have a gap. And we can adjust the size of each one of these. Obviously, we need to adjust the size of the star aperture so the star is entirely in that and get a reasonable measure for the sky annulus so it doesn't cover up other stars. So the star aperture gives us the photons coming from the star. The sky annulus gets us the sky brightness. and the gap just separates the two. This is where Mathematica's graphics capabilities are very useful, because we can easily generate masks to do that with just a few lines of code. For instance, the star aperture, we're just going to rasterize a rectangle and put a disk in the center. For the sky annulus, rasterize another rectangle and put an annulus with inner diameter and outer diameter. And to show you what this looks like, I'm going to show you a picture, an easily recognizable picture of some peppers. That's one of our example data. So if we, excuse me, if we image multiply the peppers by the star mask, you'll see it just isolates the center portion of the peppers. If we multiply it times the sky annulus, it'll give us this ring outside the center portion. And the difference is this gap region right here. So now that we have those things, we can do some computations. First of all, we're not interested in the whole image that we've taken with our CCD camera. We're just interested in the little bit around the star. So we have a function called isolate region, which is just going to do an image take on the image and just clip out a rectangle around the star. And then the photometry calculation, I'll just step through this because it's a little more complicated, but it's pretty straightforward. The first thing we do is we carve out the area around the star. We do isolate region on the full image. That'll give us the base image. And then we get the star image by image multiplying our star aperture onto the base image. And then we get our annulus image by multiplying in the sky annulus times the base image. So the total signal from the star, we do a total of flatten of image data of star image. This is a great thing about Mathematica. It treats images and data practically the same. So we can just take the image, convert it to data, and we're in the realm of mathematics. We can flatten it out and total it up. That'll give us the total signal from the star. Same exact thing for the sky annulus, getting the sky total. We also need to know what the area is of the annulus. So that's just pi times the outer diameter squared minus the inner diameter squared divided by 4. And then we can compute the per pixel sky signal. Take the star aperture area, the sky background per pixel is the sky total divided by the sky annulus area. And then the total signal that we're looking for minus the background is just equal to the star total minus the star aperture area times the sky background per pixel. I'm going to trip over that in just a second here. So that's the bulk of our calculation. Now that we've got our signal data, we need to know when the picture was taken. And for this, we're going to use Julian Dates. Julian Date is a very useful piece of information for astronomical observations, because it's a real number corresponding to the number of days which have transpired since a certain time in the past. And the time we take is January 1st, 4713 BC on the Julian calendar. So this is a large number of days. And it's a fractional number of days. So if you're halfway through a day, it's something 0.5. Now, as I said before, Mathematica is great for doing astronomical calculations because we can handle the type of data that we have in astronomy, which are called FITS images. A FITS file contains not just an image or image data, but it contains a whole lot of other stuff, which is in the meta information portion of the FITS file. So for convenience, I wrote this utility function called load FITS object. And what this does is it takes a path to our FITS file, and it creates an association with two parts. The first part, the image part, it just imports the image data from the FITS file. And then the meta information part, it just imports the meta information from the FITS file. And it puts that into an association. It keeps them together so we can get the Julian date and link it to the image data. Now, one bit of complexity here is that there's no good standard inside of FITS files for representing Julian dates. The simplest thing is if the meta information contains a JD tag, which stands for Julian date. So the first thing we do is we look in the FITS object, look in the meta information, and see if we have that JD tag. If we got it, we're okay. If we don't have it, we're going to try to whip it up using Mathematica date functions. So that's what this more complex version is, this get Julian date alt. And here what you can see what we're doing is we're trying to look for the date-obs tag. And if we have that, we split it either by dashes or slashes. And then we look for a time, universal time tag. If that's not there, we look for a time-obs tag. So this is all nastiness. But luckily, we can put this all together into a date object and then convert the date object directly to a Julian date using functions which are built into Mathematica. So we get the Julian date anyway. So one more bit of complexity here. So now we want to be able to extract the brightness as a function of time. So we have this function here, photometry obs, and this will give it a FITS object. We'll give it a list of coordinates in rows and columns where the star is located, a comparison star coordinates, because we've got to make these observations relative to a non-varying star, and the magnitude of the non-varying star, and then the diameter of the star we're looking at, the gap diameter, which is the outer part of the gap, and the sky annulus diameter. So this is pretty straightforward, though. First, we get the FITS object, the image object out of the image. We get the Julian date out of the FITS object. And then we do our photometry calculation on the star. And this will give us the magnitude of the star based on the star diameter, the gap, and the sky diameter. Then we'll do the same thing to the reference star, find the difference in magnitudes, and then we'll return a list comprised of the Julian date and the differential magnitude plus the comparison star magnitude. So now finally we got those tools put together, we can actually crunch some data. So right now I'm using data that came from the University of Iowa, some of their example data for studying Cepheids. So now we can just use Mathematica to put all this stuff together. So we get our file names of our directory of our FITS objects. Here they're star.fts. I've loaded the Cepheid images. And this is the region of the sky we're looking at. And University of Iowa has kindly pointed out where the variable star is, and where our reference star is. And we can take a look at the first of our images. And so there's the star field. And if you look carefully, so there's our Cepheid, and there's our reference star over there. And we can pick up the coordinates of this simply by just clicking on it and using our coordinates tool to pick out the rows and columns of our target star and our reference star. So once we got that, we can just, and assuming the star fields are all well aligned, we can compute the photometry on each one of the images. And this will take a few seconds here. But it's pulled those in and it's done the computation with the reference star at magnitude 10, the diameter of the star mass 6 pixels, an 8 pixel diameter gap, and a 20 pixel diameter annulus. And it sorted those by the observation time. So they're all in sequence, although not necessarily evenly spaced. And that's a significant thing. Let's see. Yeah, so the first of the data points here, you can see the Julian date is 2.45454 times 10 to the 6, so about 2.45 million days since that time in 4000 BC. The magnitude of the star is 10.7252 at that observation time. So now we're getting somewhere we can actually plot the light curve. And the way I like to do it is I take the first date and I subtract those off. And if we plot that, we can get the light curve of the star over a period of 20 or 30 days. And you can see that the period of this, and this is a classic Cepheid light curve, the period's about 14 some days. This is list line plot. So list line plot, I can do just a list plot, and let's see what that looks like. Oh, yeah, right? That's my, yeah. So that's our data without the lines. It's a little harder to see the pattern there, but that's why I put the list line plot. Okay. So so now we want to find out what the period is, because that's what we're after. So there's a couple different ways to do this. And the first thing I tried was just using a find fit on the data. And this will give us, so the function I tried fitting was this, mv, ib sub v plus a sine of omega t plus phi. And we're looking for those parameters as a function of time and have the offset sorted data. And this gives us mv, which is the apparent magnitude of the variable star. That's one of the things we're looking for. However, find fit isn't the best function for determining the frequency of a fit to periodic data. And unfortunately, we can't use fast Fourier transforms for this because those require the data points to be regularly spaced. And astronomical data is almost by definition not regularly spaced because observations will have to be done over a period of days or weeks. There might be clouds, the moon might be up. So we can't do that, but we need another more powerful tool. Now, luckily we have such a thing, and it's available in our function repository. So to use this, we just have to split out the observation dates and the observation values. And we have to offset them by the mean because it needs to be zero offset. And then we can use this irregular periodogram function, which, by the way, the mathematics behind irregular periodogram were done specifically to aid the processing of aperiodic astronomical data. And it's available in our function repository. We can go to the page for irregular periodogram. And this page has oodles of good examples for this, and I invite you all to get on this and play around with it, because it's exactly what we're looking for. So if we use that and plot it, we'll see that there's a strong peak corresponding to the fundamental frequency in the data. And it's about 0.4 something radians. And we can use Mathematica to determine the exact position of that peak. And it's 0.43 7824 radians. And the period, you can see, is about 14.35 days, which is what we looked at from the chart up there when I plotted it. So if we plug this into our distance from period formula, we'll say that and assuming that the observed visual magnitude is 10 point something, we can get the distance in parsecs to the Cepheid is about 12,000 parsecs. So before I mentioned that this is dependent on having images which are rock solid, because we have to compare this target star from image to image. And if it swims around, it's not going to be any good. So how do we solve that problem? Well, real star fields tend to swim around a bit. My colleague Jeff here has graciously loaned me some of the images that he took during his graduate work of variable stars. This is not a Cepheid. It's a eclipsing cataclysmic variable star. And this is what it looks like. You can see it fade in and out there. It's right there in the center. But it's also kind of swimming around. And why does it do that? Well, it's because astronomical instruments have errors in their gear trains. And even with good tracking, you're going to still see a little bit of a variation in position. And in order to solve this problem, we need to align the images. And we can do this, again, using Mathematica's image processing capabilities. Now, I'm not going to walk all through this because I've talked about this before in other talks, but we can use Mathematica to pick out features, in this case the stars, and then from that extract a set of transforms which we can apply to successive frames. And once we have done that, we can, and those are some additional functions, we can use that to align a series of star frames. Like, for instance, here is an image of BL Camelopardalis, and you can see that it's swimming around a little bit. But after we apply this alignment function to it, you can see it's rock steady. You can see they're fading in and out a little bit, but I haven't done any more processing on these things, and we could do more work on that. So and you can see that we can do an image adjust on that, and then if we extract the light curve from this, and it'd be better if we had more good images so we can get a better light curve, but you can see that we're getting, this is more typical of data that you might get. And if you have a lot of things and you feed them into the periodogram function, we can get a pretty good idea of what the period of this is. And from that, we can extract data about the light curve. And you can use these same techniques, as I said before, to extract other types of light curves, like light curves that come from eclipsing binaries or from exoplanets. So, but that's really a subject for a later talk, and so I think that's about all I want to say for right now. So I think we got maybe a minute or so for questions.
Is the bottom line plot there showing a period?
It's a little hard to say. It's because I don't have enough images in this data set. I just kind of pulled this off the internet, but you can see it's part of a light curve of some. This is more typical, and when real astronomers do this sort of work, they collect hundreds of images, maybe from different telescopes on these things, and so what you see is a very heavily populated light curve, and then you can extract a very good set of data from that and find a good period. I'm getting to that. As I said, I'm an amateur astronomer, so I'm constrained by things like clouds and trees and stuff. But I'm planning on doing that this spring. Yes, sir.
Levitz did all this by eyeball?
I think they did. The way they would do this is from my limited knowledge, is they would look at plates and then they had comparison images of like stars of different brightness. So they could say, if they wanted to extract the magnitude of a star, they would compare it to a comparison plate and say this star is about this magnitude, and that's how they got the magnitude information. But you can imagine doing that for the dozens of these big glass plates and with a microscope, and it really makes you respect the efforts of these people who did this.
But it also depended on the procedure to develop.
Right. So they would have to extract this data, and then from hundreds of observations, you can get information about the period of the variable star. Any other questions? Okay, well, I think that's it.